Welcome to the webinar Introduction to Statistics on Structures, also known by the acronym SoS in version 3.2.1. My name is Christopher Zechmeister. In the next hour, I would like to present you our software product in its current version. I've muted you to avoid any background noise, so if you have any question during this presentation, please use the questions and answers window of your client. I will review them after the presentation and will try to answer all of them. Another block of up to 30 minutes is therefore reserved. This presentation is split into three parts. With respect to the last webinar in April 2016, I'm going to replace the very basic introduction into the topic of random fields by some less theoretical introduction about the usage of random fields in robust design optimization. Afterwards, I will show you some successful application examples using our software Statistics on Structures to analyze such random fields. And finally, I will give you a short software demonstration. Fine. So let's start with some notes about the robust design workflow as propagated by Dynado. One should start with a sensitivity analysis at the very beginning, which means computing the outcomes for different input parameters in some finite element simulation or measuring some quantities for different production settings. This might be already quite known for scalar input and output parameters, but obviously can also be done for field quantities on input as well as on output side using SoS. Building a so-called meta model afterwards helps one to identify important parameters, which means parameters it is worthwhile to take into account in further analysis steps like a multidisciplinary optimization, defining some sort of criteria, for example, minimizing the error norm between the reference and the design signal. Already at the optimum, one might now define uncertainties on the input side, validating the robustness of a product with some variance-based criteria. I would like to show you in this introduction that random fields might help one essentially in each of these described steps. Let's take a closer look at the definition of uncertainties like a signal output, which is nothing else than a one-dimensional random field. This output could be a Euler curve, some stress strain curve, or some dynamic loading. Working with random numbers, one would pre-select some a priori hotspots, like this one, reading information only at these points on output side. As most of us are used to random numbers, they are easy to understand and have simple statistics. But we need some time and extra software to extract our a priori hotspot information, and above all, in most of the real-world examples, hotspots will vary in position and our a priori selection will be likely wrong. And we get no information at all on the shape between our a priori selected points. The same arguments can be listed for three-dimensional random fields, which might be found in the quality control of some production step or in outputs of finite element simulations like plastic strains. Even here we are used to pre-select some points of on our structure, losing the essential information about the shape between these points. We are spending time and the results are likely unsatisfactory. But, as already announced, there is an easier and less error-prone workflow available using discrete random fields and statistics on structures. With SoS, one does not need to identify any a priori one-dimensional or three-dimensional point. We take the uncertainties on the input side, which might be already well-defined random variables, building a robust sampling and evaluating finite element solutions of discrete measurements afterwards using SoS. Only in this manner one might be sure to get reliable hotspot information. Then we might continue with more detailed statistical investigations at these hotspots, like estimating the distribution function, checking input parameter influences, and so on. Or one might investigate further statistics directly on the discrete random field, like exceedance probabilities. How can one define discrete random fields? either one-dimensional, for example some signal over the time, or three-dimensional, like in this example visualized on the right side. To base a discrete random field simulation on some reliable statistic, SoS would need some dozen of random field realizations. So if you have many measurements or the result of many finite element computations, SoS can automatically generate an empirical, anisotropic, inhomogeneous, and even a non-Gaussian random field model, like mentioned in the third point. Otherwise, if no output at all is available, one can still investigate his field with the new synthetic random field model. For example, even if no measurements for geometric deviations are available, one might still generate new disturbed geometries. And if one has at least some measurements, like 3 to 5, he can use them to determine at least an empirical mean and standard deviation vector. Knowing why random fields are essential quantities, it might be now quite interesting how SoS represents them internally, or in other words, how SoS finds automatically an optimal parameterization for a given set of signals like load displacement curves and so on. Its root in descriptive statistics, SoS has been developed to read in many realizations of a discrete random field and represent them automatically by the very fast and accurate Caron-Loew expansion, which is shown on the bottom of this slide. Here we have our UE, for example, or one realization. This spectral decomposition of a random field starts with the invariant mean value and represents any variation with invariant so-called shapes multiplied by a set of uncorrelated random numbers, the so-called amplitudes. So although we are starting with a discrete random field, we end up again at a representation with random numbers, which we are already quite used to deal with. On this slide, you see at the left bottom figure a design of experiment with about 100 signals. On the right side, you see the Caron-Loew expansion with 5 shapes already sufficient to represent at least 99% of the variation within the design of experiment on input side. Are there further advantages of using the Caron-Loew decomposition within statistics on structures? Of course. One might now generate new random signals as solver inputs. All we need to do is to vary the random variables within our representation. And as we are dealing again with random numbers, we can apply all the methods of OptiSlang, performing sensitivity analysis and pre-optimization on metamodels. In the software demonstration, I will try to show you how easily this can be done and what advantages you will have doing so. Obviously, statistics on structures is not only limited to one-dimensional random fields. It can handle also three-dimensional ones, like shown in this example. Especially, field variation might describe displacements, plastic strains, thinning, and so on. SoS treats it in principle like a one-dimensional random field. For the parameterization of a three-dimensional random field, let's take a look at the buckling problem of some car string. The left plot shows you the standard deviation of the plastic strain field. On the right side, you see the Caron-Loew expansion with 3 shapes already sufficient to represent 99% of the plastic strain variation. Getting closer to the software demonstration, let's highlight some key features our software statistics on structures is known for. Obviously, SoS can visualize statistical properties on a three-dimensional reference structure. SoS can handle random fields on input as well as on output side of a workflow. And SoS finds automatically the optimal parametric to describe field variations. With this parametric, it can further generate new random designs. It can predict field responses, varying field input parameters. It predicts the field response in real time, and its parametric can be easily used to identify important input parameters. SoS can be easily embedded into an OptiSlang workflow to generate new random designs or to predict, for example, some distributed loading on the input side of a finite element simulation. Due to its batch driver capabilities written for the Lua scripting language, it can be even embedded into any other workflow management environment. And starting with version 17, SoS can also be used directly within ANSYS Workbench to automatically update the model component of any system. This first listing of key features of statistics and structures concludes now my introduction. To demonstrate you that this is not at all just empty rhetoric, let me show you where statistics and structures has been already successfully used to handle discrete random fields. The first demonstration example is a medical one and shall give you an impression of the before mentioned automatical parameterization of geometry variations with SoS. Given where 60 measured mandibles where the teeth have been erased from the model and the measurements have been transferred automatically on a reference CAD mesh before proceeding with SoS. Afterwards, SoS simply created an empirical random field model for all displacements measured from the reference mesh to each measurement. Let's have a look at this automatically generated random field parameterization. Remember, SoS uses the Caron-Loew expansion, which consists of the mean value, the shapes, 4 are already sufficient in this case, and the amplitudes, which are random numbers currently all set at 0. So actually, the random field model on the right side shows the mean value only. SoS will now automatically adapt the amplitudes of its random field representation to match the measurements, which will show up on the left side in the following short video sequence. I think this was a really impressive first demonstration of random field capabilities in statistics and structures, and I would like to thank once again Mr. Wright for providing this video. The next demonstration example shows one of the motivations why statistics and structures has been developed at all. Our customer wanted to build a finite element model where he could virtually investigate measured break squeal noise. He already invested some time to parameterize this model to use random variables on input side. He even used another analytical random field model formulation. But still, he was not able to reproduce these measured frequency windows. With SoS, we built an empirical discrete random field model based on real break pad surface measurements and generated new designs in the preferred target solver format, ready to be included in the customer's solver environment. And indeed, the inclusion of random field representation of the break pad surface was the missing part to generate designs which simulated break squeal noise in the observed frequency window as shown in this slide. The blue points indicate random designs generated by SoS and the red ones former approaches. Where former efforts failed to virtually reproduce observed frequencies, the empirical random fields approach succeeded. This example shall demonstrate the use of statistics and structures on a one-dimensional discrete random field for a quite known consumer good, a VLAN antenna. Given a lot of solver output files of a previous design of experiment run, the task was to parameterize the one-dimensional random field output, the signal itself, and to minimize the signal loss at 2.4 and 5.8 GHz. Using SoS and OptiSlang, one builds a field meter model to link antenna design parameters to the amplitude values of the empirical discrete random field model. Just as a side note for those who are not familiar with meta models, a meta model is an approximation of some real process which correlates input parameters to their outputs. So it's very useful to analyze, for example, which input parameter influences a process the most, or to replace an otherwise a very expensive process computation. To come back to our application example, here we use the meta model to link the antenna design parameters to the signal loss, which have to be minimized at predefined frequencies. On this slide, you see the field meta model prediction quality. Here you have the output of the SoS prediction, as well as, which cannot be seen, it's a second red curve below or exactly above the SoS prediction, which shows the real solver output. Those already knowing some scalar software like OptiSlang could point out that also the parameterization task could have been done manually at pre-select abscissa points, as I also mentioned in my introduction. On the other hand, using statistics on structures, one does not need any a priori point, but can use the whole abscissa. And to be honest, which hotspot or even which group of points would you pre-select around the singularity at 2.4 GHz? It's simpler, less error-prone, and especially more accurate to use a random field model for this task. This slide is a rather general example, as it shows especially output to sensitivity analysis, precisely the output of our field meta model. All these plots tries to help one identifying which input parameter influences the output the most, and particularly at which mesh position. Furthermore, it gives one information about the prediction quality of the meta model. For example, the most upper curve in the signal plot describes at which interval the meta model describes fits very well. All the other curves in the signal plot are related to important input parameters, showing at which interval they are influencing the signal to which contribution. For example, this curve influences the signal at this interval the most. The three-dimensional plots at the bottom doing the same, plotting the influence of an important parameter via color directly on the three-dimensional structure. Fine. I hope I could show you some interesting demonstration examples. We are now ready to start with the last exciting part, the introduction of our software product itself and some live demonstration. Before actually opening our software, I would like to add a few additional interesting notes. SoS uses finite element meshes to represent and visualize its discrete random fields. This slide simply lists the essential information which commonly known solver languages and their mesh definitions are actually recognized by SoS on the import side. You will find here widely used formats like ANSYS Mechanical, LS-DYNA, Abacus, and the general STL file format specification as often used within measurements. The next slide tries to summarize the current capabilities of SoS in one short sentence. Use SoS to analyze and simulate distributed variations. What includes the term analyze? Analysis of measurements or simulated data from a previous design of experiments run, determining a random field model and analyzing the influence of process input parameters using a field meta model. What means simulate? In combination with OptiSlang, one can generate new designs, an example for robustness analysis, and one can replace an eventual expensive process solver code by the field meta model solver, an example for an optimization workflow. Distributed includes 1 to 3-dimensional random fields like signals and unstructured finite element meshes. Now it's time to open statistics on structures the first time. So let's minimize the presentation. I've already opened an instance for you and skipped the import wizard, as for now I would like to show only the graphical user interface. The main window in SoS is split into 3 modes: the edit, the visualize, and the command log tab. The logger and the command line at the bottom are visible in all these modes. The command line can be used anytime to issue a command dedicated to the SoS kernel. As already mentioned when talking about the batch capabilities of statistical structures, the kernel of our software may be fully controlled via the scripting language Lua, which has been extended by special commands regarding SoS functionality. Every time the user selects any graphical user interface command, there will be written and executed some script code in the background. This script code may be seen switching to the command log tab. The scripting language is also the reason why SoS can be easily integrated in any existing solver chain. Back to the Edit tab. The toolbox on the left side contains all commands to manage any data type and to start some annotation, like computing the field mean value. The Visualize tab is obviously used to plot and check field data on the reference structure. In the so-called inspectors on the left side, the user might control a lot of scene settings. Okay, let's have a look at one of our demonstration examples used throughout the remaining software demonstration. During a default installation process of statistics on structures, a couple of simple demonstration examples are placed into the public document folder. In this demonstration example, the sheet metal forming production process of a shell structure was simulated using LS-DYNA as numerical solver. We ran a robustness study with 100 designs varying some random numbers on the input side. These random numbers include material definition, shell thickness, as well as the process velocity. The process setup itself is illustrated in the feature on the left. Due to symmetry of geometry in loading, only a quarter of the structure is modeled, counting about 10,000 elements. During the production process, the punch is subject to vertical motion. Since all bodies except the blank are rigid, the blank will be deformed into its desired shape. At the end, the rebound phase is initiated by removing top and binder and shifting back the punch. The blank will rebound to its final geometry. Looking at the result of one of these designs, we can also visualize the process as shown in this animated picture. Next to the data distributed with an SoS installation, I've also prepared some STL files of the final geometry for this webinar. The STL file format seems to be a quite usual file output format for measurements. So for those of you hoping to analyze some production data, I would like to demonstrate that SoS is also able to work with non-matching meshes. Therefore, I would like to start importing these STL files first and map their geometry deviations on our finite element reference structure. This time we open a new instance of SoS. SoS presents us the start wizard right at the beginning. Let's minimize the presentation. This wizard guides one through some default actions like loading a previous project, executing a script file, or starting a new project, as we will do right now. The first thing SoS asks for is, of course, the reference mesh. The reference mesh is one finite element mesh all data objects are projected on during import. Furthermore, it gets used to visualize inputs as well as output fields. So let's navigate to our demonstration example directory in the public documents hierarchy. Okay. LS-DYNA metal forming process, the deep drawing one, robustness. You already know the reference mesh is important as every field data will be associated with it. So although one can choose any mesh of this DOE, you should choose one without missing mesh items. Therefore, we copied one of the design meshes directly in the project base path. Typically, SoS defines a file system filter for every dialog, so to see the prepared reference mesh, we need to change the solver input format to LS-DYNA. Here we have the prepared reference mesh. We could further define some project name, and we would also be able to instruct SoS at this point to open the import field design wizard to compute some basic statistics like the mean and to determine the random field model. We won't do that now, and we'll give project name webinar. Finish. Okay, SoS has already imported the reference structure. We can now switch to the Visualize tab to see or to verify the reference structure. The Scene Manager presents us also some additional mesh information in the legend, like the number of parts, how many elements and nodes, the largest dimension, and so on. Okay, let's associate some field data to our reference mesh. Therefore, we need to change back to the Edit tab. And to choose the Import Field Designs command in the Import group of the toolbox. The wizard opens. First, SoS needs some directory templates consisting of a design directory base path, and its subset of files of interest. If you are loading any data from an OptiSlink project, this is a straightforward process as SoS extracts automatically all the information it needs to parse the project path recursively. Otherwise, one has to correct the base path manually. You should always start to simply add your files of interest. So let's do that now. We wanted to start with the STL files, which should be located at desktop. Oh. No. The link is broken, unfortunately. Let me remember the path. Yeah, it should be also located here. Just a moment. We need to switch the file format to STL files. Yeah, here we are. And let's select the STL format. As I have now parsed the file and presented some additional information, it's an STL geometry, so SoS merged automatically vertices and triangles. This is an information only, so we can hide the dialog. Here one can see which information has been found in which file, and we can choose a user-defined import ident at the bottom. Furthermore, you may notice that SoS automatically recognizes the correct base path. By default, SoS assumes that any design mesh information is compatible to the loaded reference mesh, as it is the simplest and fastest import case. As mentioned in the introduction of this demonstration example, in the first step, we loaded STL meshes from an assumed post-production measurement. These files are definitely not compatible to our finite element reference mesh, so we need to choose one of our mapping algorithms. Differences and theoretical principles are all explained in some detail in our built-in help system about these algorithms, which I would like to show you at this point. So let's close the field design wizard. Never mind, SoS will automatically restore all the settings done so far when we reopen this dialog. Let's double-click on the overview on selected algorithms. Here you find assistance, including some features to choose appropriate settings to import and map your data on the reference structure. Okay, going back to the Import Field Designs wizard. We now choose the closest point projection mesh mapper, assuming a smooth boundary. In the Settings dialog, we might refine some essential settings like the search distance to either speed up the process and to improve mapping quality. We know this example, so we also know that 10 or let's say 100 is more than enough. We further deactivate the coordinate divisions along boundary normal to get sign distances. And in case of a real measurement, one might expect that the measurements are shifted and rotated. with respect to the reference mesh. If this would be the case, SoS offers some algorithm to automatically adjust the design coordinate system. Otherwise, our mapping algorithms would fail or produce some nonsense output. In this case, we know that the STL files are exactly at position, so we can close the settings dialog now. Furthermore, I want only import the normal coordinate deviation, so I can deactivate all the other import items. Okay. All settings are done. We can now proceed to the next page. As SoS fully recognized the naming scheme, it automatically found the correct settings to import all designs. SoS recognized 101 designs within the base directory. At this point, we could further reduce the number of imported designs manually or by loading an OptiSlink binary file, which might know the failing state of some of the designs. We could also change the design directory format string if we would work within an ANSYS design of experiment. We proceed here without changing anything except the design directory ranges. We only need the first 100 design. The last design has been calculated by OptiSlink, although it's just the reference design. Okay, let's finish. Although the import process in SoS is quite fast, currently the software is importing and mapping about 2 to 4 STS files concurrently, this procedure will take about 1 to 2 minutes, which I'm not going to waste to simply wait for it. So I've already prepared a ready-to-use database after the import process, which I would like to use now to continue my presentation. The import process might still run in the background. Okay, the database should be here. Here we are. As now some data is present, we could check some information on the imported designs. Therefore, we need to change the visible data type to samples and results. We have here the quantity information table, which already gives us some information. We have 100 samples imported. And there is no random field model built yet for this field quantity. Let's change to samples and results. Here we have information to our imported designs, and most of them, or all of them, have a yellow exclamation mark, which indicates that we have missing items, which means the projection algorithm missed some elements, not succeeded at some of the elements to project the data on our reference mesh. We can either check how many elements these are in the data object information on the right side. Missing items 179, that's not so much. And we can also check this information in the Visualize tab. Therefore, we load the data object by double-clicking into the Visualize tab. And within the inspectors, we can change to the mesh inspector, and data kind can be set to missing. So we have complete and missing information, and the data interpolation could be set to element. So we see that only boundary elements failed to be projected correctly, which is not that problem. So we so this projection can be seen as succeeded for now. Let's switch back to the Edit tab. And now we could also do for the first time some statistics, like computing the standard deviation to check at which positions or at which regions of our demonstration example we have some variation in the structure. And we could also select maximum sample values, which means taking at each mesh position the maximum value of all designs. Okay. Let's switch back to visible data type results only and visualize these two scenes. I prepare the Visualize tab with two scenes and load both of them concurrently by selecting them with the mouse and hitting the Enter button. Let's rotate and move the scene as we need it and sync this camera position. Here we see that most of the variation is at the bottom of the demonstration example, which might also be already expected. And we could select also some largest variation points, some hotspots, to say it. This can be done in the selection inspector on the left side. We switch to it. We can change the number of pre-selected points. We will take the default value, which is 5, and select the 5 largest value of local maxima. Would be this one, with the corresponding values. If we would verify or check something on the left scene, we could also sync this selection to the other scene. This is, for example, useful if we try to validate a finite element data model. This can be done in Manage Views. Here we have the sync selection. If we would have selected the right scene, let's redo that. We have selected the scene with the pre-selected points and sync the selection to the other scene. Okay, so far so good. Let's import some new data. To get to the main feature of statistics and structures, its capability of analyzing random fields. If you have many measurements or the results of many finite element computations, SoS can automatically generate an empirical random field model. Otherwise, we can make some good assumptions and generate a synthetic random field model. And if you have a couple of measurements only, you can at least use them to determine an empirical mean and standard deviation vector, as already mentioned in the introduction. As we do have enough data from a design of experiment run, we can use the key feature of SoS, its empirical discrete random field decomposition. So let's import some additional finite element output data for this purpose. We open the import field design wizard and add some plastic strain fields as our file of interest. Let's add the file, not in the webinar directory, but in the public folder. As we are switching back from the STL and measurement topic to the finite element simulation. Metal forming, deep drawing, robustness. In design 001, we take an LS pre-post output file, the plastic strain field. Okay, that's imported. SoS again automatically split the path in the base path directory and the relative directory to the file of interest. Now it's a compatible mesh, so we only need the compatible mesh mapper. And we change the imported item to some shorter one, the pstrain. Okay, that's it. Let's continue. We import only 100 designs. Finish. And the data is already imported. Okay, here we are again and ready to proceed with the Carbon-Löw decomposition. One finds the proper comment in the random field model toolbox on the left side. Let's select the pstrain field quantity first and press the comment button afterwards. In this dialog, one can now determine the the desired explainable variation, and one can also limit the number of shapes to be used. Just as a guideline, if the random field model shall be used in a maker model, the explainable variation should be explained by more than 99%, whereas more than 90% would be already sufficient to simply generate random designs. The options below control additional information output only, whereas the cross-correlated option is reserved for advanced usage. So for this decomposition we are done, and I press the OK button. The computation shouldn't take that long and is already done. You might have noticed a warning log message in the logger below. Let's see what happened. I will try to increase the logger output. We limited the current expansion to 20 shapes, but required a random field explaining of 99% of the variation. SoS now informs us that we would need more shapes to reach this target value. For now, we will simply ignore this warning, otherwise we could simply rerun the decomposition. We would see that the numbers of vectors to match desired variation is 28. Okay, let's minimize the logger again. What else can we see? Associated to each shape, SoS brings the cumulative variation. So the first shapes already explains about 60% of the design variation. The second shapes adds about 20% to this explanation, and so on. And with 3 shapes, we would already explain more than 90% of the variation, which would be enough to, in example, simulate a strain field as input for a subsequent solver run. To check the accuracy of the random field, one can compare the standard deviation with percentage of explained variation. Doing so, we have to calculate the field standard deviation and sending both results into our visualization. To compare these results, it would be then the best to visualize both scenes next to each other. Okay, the standard deviation is already computed for the coordinate deviation normal, but not for the p-strain field. So we need to compute it in the statistics box. And then we can visualize the standard deviation as well as the variation next to each other in the visualize tab. Here we are. Let's move the structure to see it better. Fine. Syncing the camera again. Here we do have the variation of our imported random field, and here we do have the quality of the random field decomposition. Green means very good, and red means not so good. So let's check if these red elements are a problem or not. In the variation scene, let's select with the selection inspector again the 5 largest local maxima, which are at the features of this structure. Here we have the most variation, and synchronize this selection to our p-strain variation plot. Here we see very, very good values, near to 100%. So our random field decomposition explains about nearly 100% of the variation in the design of experiment imported. What about these values? Let's select now one element in this scene and synchronize it to the other one. Close the camera. Here we see that we have nearly no variation. And if you remember, our field meter model, our random field decomposition adds only the variation of the field imported. So if we have no variation within the field, our random field model does not need to explain anything. So this is not really a problem. Okay. New to this version is the Visualize Random Field Variations command in the Random Field Model toolbox. This command can be used to change the field amplitudes and to visualize these changes live on the reference structure if needed. This might be useful to visualize some local effects of higher shapes. Let's start this command just for a second. We pre-select our quantity, change to the Random Field Model toolbox, and activate this visualization. Let's switch back to only one scene and rotate the structure as we need it. Here we do have another inspector, the Random Field Inspector, with our amplitudes listed currently all set to 0, so we do have the mean structure plotted on this side, in this scene. If we would now change the amplitude values, we could investigate some changes in the structures if we would change the palette settings here. I won't do that now, because it's just a demonstration of this quite nice feature. I would like to show you another new command in this version, which is the synthetic random field model. I've already told you something about that. When do we use a synthetic random field model? We use it when one has no measurement. How can we do that? That's quite simple. If a reference mesh has been imported, as it is now, one selects the command in the random field model toolbox. Here we have it. Here we have to define a field quantity ident and the data type first. We already know the other options about explain variation and maximum number of shapes. As we do not have any designs to extract the correlation structure from, we can assume that, we have to assume one this time. The default model type is also the suggested one, and about the correlation length. The smaller the correlation length is set, the more local effects are desired and the more shapes will be needed to get these effects. Furthermore, we either define homogeneous mean value and standard deviation, and we need to define the ident now. Let's write synthetic p-string. So we need the data type element. And we leave all the other settings as they are default, assuming that we have no design at all to work with. Okay, that's it. You will immediately recognize the difference to the empirical random field model if you are looking to the data object table. We need 7 instead of 3 shapes to describe 90% of the variation, and if we visualize one of the shapes are trigonometric functions only. So take a closer look to the first shape. Let's switch back to 2 scenes. Erase all the other ones. Yes. We select these 2 shapes and press the enter button. Here we are. This is the empirical one. And this one is the synthetical one. But if no information at all is available, then the synthetic random field model is nevertheless a good choice to investigate the structure, to investigate how the structure reacts on changes, for example. Another essential feature of SoS is its capability to global spatially sensitivity analysis. I've already prepared the database for our demonstration example, and I would like to show you how SoS can help you now identifying which regions will be influenced most by which parameters. So let's open this predefined database. The data object table immediately presents you the most important input parameters, and to which degree they influence the desired response. And this response is, in our case, the plastic strain field. It's always a good idea to check the quality of our field meter model. Doing so, we open two things and face the random field sigma to our total field UV value. We have to select the total field UV value and the random field sigma. Let's change to the Visualize tab with two themes. Let's the enter button. The themes got rendered. Again, we have the variation of the random field on the left side, and on the right side we have the field meter model prediction quality. Check again. We have variations or regions of interest where we have a lot of variation. And how is the FCUB value at these regions? It looks quite good. Let's check that one again with our theme selection. Center selection. Yeah, the values are all good. And again, there are some red regions, but at these elements we do not face or only a little bit of variation. So this doesn't bother us. What else can we do? Let's erase these things, switch back to the Edit tab. We could check the influence of one parameter to our plastic strain field. Let's take the influence of the largest influence of one of these parameters, and the parameters with the largest influence has been identified as the vertical velocity of the punch. Let's visualize this one. And without doubt, and as everyone would have expected, this parameter influences the structure the most at the features of our demonstration example. Okay. As already promised to you several times, we can also detect hotspots in a simple and fast manner. Hotspots are nodes or elements of interest, typically measure regions with large scatter. Hotspots might be of interest in simple robustness analysis, like determining the exceedance probabilities, or in an optimization task, like the minimum and maximum values among all samples. Let's switch back to our database with the P-strain field, as we have imported before, should be that one, the webinar. No, that's not true. It's the other one. I've lost myself. We proceeded with that file. Yes. So if we want to check the exceedance probability of some given limit state, for example, we could use the appropriate command from the statistic toolbox. Let's take the P-strain quality again, and in the statistics toolbox, we take the quantile command. We could now compute the 95% quantile for the P-strain quantity. Let's do that and visualize it. Okay, let's select one of the elements. Picking any element, we get now the following information. 95% of the values associated with this element are below this given value. Now we can change the palette settings to plot regions which might exceed our defined limit state. Let's define one. Let's say our limit state would be at 0.39 for the plastic strain. SoS now plots the elements which would exceed this value. We can further We can further change the palette settings to traffic light to get a better view to these elements. Okay, now we could select some of them. Let's say, again, the 5 largest local maxima. Here we are. And we could export them via create scalars and export to OptiSlang for further investigations. Export selected scale, export scalars to OptiSlang here. And in the post-processing of OptiSlang, we could estimate distribution functions, check correlations to input values, and so on. Okay. At this point, I need to end my presentation to summarize again some key features of SoS. SoS provides the possibility to visualize statistical effects on structures. SoS finds automatically an optimal parameterization to describe field variations. It can generate random designs with distributed scatters and can be used for sensitivity analysis. These are some of the key features. I hope I could show you that discrete random fields are nothing for experts only, and one can face them quite easily in typical product development. And with statistics and structures in its current version, everyone gets a tool in his hand to easily deal with them. Okay, as there are no further questions, I proudly assume that my presentation was already to your satisfaction, and I would like to thank you for your attention and close this meeting now. Thanks again.